Thank you all for coming. It is my great pleasure to introduce Professor Rice here. And Professor Rice got his PhD in Cambridge in 1964. And after that, he visited many places. And particularly, he spent 15 years at Bell Lab. And at some point, he was the research head of the theoretical physics there. And in 1981, he became a professor at ETH in Switzerland. And Professor Rice has a long list of honors, and particularly is a member of the National Academy of Sciences. He's a winner of the John Bardeen Prize. He's a member of the Royal Society of Britain. I won't name all of them, but he has a long list of honors. And Professor Rice did a lot of important works in the field of superconductivity. So he's really the person to talk about this subject today. And particularly, so he will talk about this high TC superconductors, and which is a very complicated material. And Professor Rice, together actually with Professor Fuchun Zhang here, they formulated the theory of this Zhang-Rice singlet, which greatly deepened and simplified the understanding of Cuprate material. So it is really my great pleasure to have Professor Rice here today. And in the past 2 weeks, I really had the privilege to talk to him almost every day. And I really found him an encyclopedia of superconductors. And I asked him many questions and about superconductivities. He answered them all. It's simply amazing, and truly it is my great pleasure to have him here today. And so he will share with us his wisdom about superconductivity. Let's welcome Professor Rice.
So thank you, Vic, for that very nice and very flattering introduction. I've enjoyed my time here too, and it's been a very stimulating couple of weeks, and there's still another week to go. So, but today I would like to talk about the question about superconductivity. As I wrote up here, superconductivity is the most spectacular effect in condensed matter physics. The fact that you can transport an electric current through a mile of dirty metals without loss is, of course, a very spectacular effect. But compared to other topics in condensed matter physics, like magnetism and semiconductors, the effect on our day-to-day life has been very limited. Semiconductors and magnetism and all that's come out from these fields has, of course, had an enormous impact on our day-to-day life. But the superconductivity is limited by the fact that it has a low transition temperature, and this has limited its applications. Now, there was a spectacular effect almost 30 years ago when these high TC Cuprate superconductors were found, actually close to Zurich in Switzerland. But since then, we haven't been able to raise the temperature, and I'll discuss the reasons for this. What is the outlook for the future? So I'll begin with TC in the conventional Bardeen-Cooper-Schrieffer superconductors, which have been around for well over 100 years, following the work of Kamerlingh Onnes in the Netherlands. And then I'll talk briefly about unconventional superconductors with low TC, then about high TC unconventional, the Cuprate superconductors, and discuss then what happens if we try to look at other oxides, for example, vanadium oxides, which we might hope, since they're just analogous to cuprates with one hole in the 3D shell, these have one electron, and what happens when we try to look at these, and then make a couple of very crude speculations about future directions. So the basis, when when the first superconductors were discovered over 100 years ago, of course, it was a great surprise. But then people really didn't understand much anyway about metals and about electrical conduction in solids. It was really quantum mechanics that opened up a whole new window and explained a lot of things about it, that we have electrons moving through an ion lattice and interacting via Coulomb interactions. And quantum mechanics then, in the 1920s and early 30s, changed the whole outlook of the subject. The idea that a wave, electrons were waves, have wave nature in quantum mechanics, and they can propagate through a periodic potential, forming these energy bands associated with the periodicity. And an energy band will hold two states because of the spin of the electron. So if you have an odd number of electrons per unit cell, you generally get a metal. If you have an even number, you get a semiconductor. And the difference between metals and insulators and semiconductors and many other things became clear after the discovery of quantum mechanics. You might worry, or people worried, that the electron-electron interaction could totally destroy this picture, but beautiful work by Landau in the mid-1950s showed how, in general, actually, the Coulomb repulsion does not act much at low energies and low temperatures. But although many things like magnetism, and I said superconductivity, semiconductors and metals and insulators were clear from quantum mechanics, superconductivity was not. And this is an excerpt from some reminiscences that Felix Bloch published in Proceedings of the Royal Society about 10, 20 years ago, about his time in ETH Zurich in the late 1920s when he was an assistant of Wolfgang Pauli. So here's what he wrote. Pauli thought that superconductivity was the only remaining matter of some interest in the theories of metals, and I should get on with it and be finally done with all these dirt effects. So he was ready to write off condensed matter physics in 1929. So then later further down he says, once in a while I thought I had indeed found such states, but it never took Pauli long to point out some error in the calculations. While he did not object to my approach, he became rather annoyed at my continued failure to come up with a desired answer to such a simple question. Pauli was noted for, what should I say, having a short fuse or not being always very polite. So then finally, towards the end, Felix Bloch writes, after the fog which had so long enveloped the phenomenon had begun to lift after many years, I could not resist reminding Pauli that the problem was not quite so easy to solve as he thought when he gave it to me. Since that time, he'd become much more mellow, so much more that he agreed. So for the students who don't find the results that your supervisor wants, you can take heart from the story of Felix Bloch. So the great breakthrough came in understanding superconductivity came in the mid-1950s. The paper of Bardeen, Cooper, and Schrieffer was a remarkable achievement. In one paper, they turned the superconductivity from the greatest unsolved puzzle in condensed matter physics. It's no exaggeration to say they turned it into the best understood phenomenon. And the idea was that at low energies, the exchange with phonons could form an attractive interaction. And if you had an attractive interaction, that this surface Fermi distribution that I showed you was unstable against pairing. And the sort of a cartoon to illustrate this effect is if one electron goes through, it polarizes the lattice, and a second electron follows and sees this polarization, so one generates an attractive interaction. And this attractive interaction then below a certain temperature can lead to a macroscopic pair wave function analogous to the Bose-Einstein condensation of bosons. The pairing amplitude in their model is essentially constant around the Fermi surface. This pairing amplitude causes an energy gap, and the specific heat, for example, vanishes exponentially. And the Bcs theory essentially explains all the features of conventional superconductors. So this is a quick outline of this theory. I don't want to go through it in detail here. If it starts with a model of kinetic energy, one electron, and then introduces scattering between these electron pairs. And the pairs are electrons with a total momentum 0 on opposite sides of the Fermi surface. And when you have an electron attraction, if you do a mean field with this amplitude, pairing amplitude as the mean field, you get a gap equation which can be straightforwardly solved, and you get a formula here for the transition temperature, which has this prefactor, which is related to the cutoff in energy associated with this attraction, because this is, as I said, mediated by the phonons. The phonons have a much lower energy than the Fermi energy of the electrons, so the Debye energy is much lower. So this is a low energy, few hundred degrees Kelvin. And here one has the electron-phonon interaction, here normalized by the density of states. So we can see from this formula that the transition temperature is enhanced by having a high phonon energy and a strong electron-phonon coupling. But you see, this therefore says you should really just increase the electron-phonon coupling if you're going to want to increase TC, you want to raise TC. But then you run into a problem that if you increase the electron-phonon coupling, that means the phonons couple more strongly to the electrons, and they can lower their energy, and before you know it, the phonons go soft. They go to negative energies, which means the crystal becomes unstable. So it's not so easy to just simply maximize TC out of this formula, because it can lead you just to a transition in the crystal structure, which in turn then lowers TC. So in fact, if we look at the plot of the maximum of TC as a function of time, these blue ones here are the electron-phonon BCS-like superconductors. And I was talking about 1957 here, you see. Well, no big effect. The discovery of the explanation, the microscopic theory, did not have a big impact on TC. It rained very slow. This is where, as Vic pointed out, the many years ago that I started in condensed matter physics, you see nothing much happened. So people were very pessimistic because they didn't look like any action in this curve here for many years. But then, in recent years, actually in the beginning of this century, a material was found which somehow was missed out by by the people looking for new superconductors, magnesium diboride, which actually had a transition temperature much higher, 40 degrees, than these ones here down around 20 degrees. And how did this happen? Well, magnesium diboride, it's an interesting material. As I said, it was discovered by Akamitsu's group in Japan, and it is a high transition temperature of 39. It's more than double, it's essentially double the previous higher BCS superconductors. If we look at the structure of it, then what we see is this is boron layers interspersed with magnesium layers here. And the magnesium essentially donates 2 electrons to the boron. So these boron layers are actually isoelectronic with graphene. which is a material which has been very much in the news with the Nobel Prize and all that in the last number of years. But the electronic structure is quite different to graphene because of the fact, or graphite, the three-dimensional version of graphene, because here the coupling between these boron layers through the magnesium is much stronger. So there is a much stronger three-dimensional coupling, and this means that in fact it's so strong that unlike the graphite and graphene carbon ones where the Fermi energy lies always in this pi band, that's the orbitals which are perpendicular, p orbitals which are perpendicular to these planes, it actually causes so much three-dimensionality that a little sliver of this sigma band, which is normally totally unoccupied, certainly totally occupied, certainly not involving the Fermi energy in graphite or graphene. And so what does that do? Well, it actually, it gives you, first of all, a very strong electron-phonon coupling because these sigma bands, the orbitals, p orbitals, are the ones in the plane. They point towards each other. So if you have a vibration which changes this distance, it enters in strongly couples to the sigma band. And secondly, these, of course, because boron is such a light atom, have very high frequency. So here with BCS theory, you can explain this. It's a beautiful example for the BCS theory. But the question is, how did it avoid this trap that I mentioned earlier of a crystal instability? And this was obtained because you just couple to a small piece of the Fermi surface and to one very specific phonon, namely this breathing mode in the sigma band. And by doing that, you can avoid an instability of the total crystal, but at the same time, you can couple these two strongly and generate a high transition temperature. So that is the reason it's actually, if you like, almost a poster child for BCS theory, but for many years it remained unknown. So the conclusion as regards BCS superconductors is that we should believe really in BCS theory. And an interesting suggestion from Warren Pickett a few years after this was discovered was that maybe one could extend the magnesium diboride paradigm by having multiple high-energy phonons coupling to electrons on specific Fermi surface sheets. This way we could raise TC. That's certainly a promising proposal, but how to realize this proposal he left open, and that's a very difficult question. In fact, it's such that this magnesium diboride is about the only material, as far as I know, talking to also to crystal chemists, that actually has a Fermi energy which cuts through the sigma band. So, it's a nice proposal. It's a nice proposal, but the question is how to realize it. So let me talk more generally about condensed matter physics. So, in a very, I keep pointing the wrong thing. In a very famous paper that Phil Anderson wrote in the early 1970s, he talked about the title of it is More and Different, meaning that if we put atoms together to form solids and liquids, we get different results than having the atoms in isolation. So if we were to compare in condensed matter physics to particle physics, which has been a topic for the last while here at the Institute, in particle physics they have a phenomenological standard model of high energy physics, which is well known and well established, and they're trying to find out where it came from. That's why they always want to go to higher energies. We're faced with the opposite problem. We know on the scale of typically of an electron volt, what the electrons, how they interact with ion lattices, and we can calculate on this sort of scale quite accurately what we should expect. But the question is, when we cool down, how do we reach, what states will we reach, what states will emerge, and can we identify and understand them? So this is the task that we're facing in condensed matter physics. Now, so soon after the BCS theory, which, as I said, is based on an attractive interaction, the question was raised, what happens if the pair scattering interaction is in fact a repulsive interaction? Should we be able to get a solution of the gap equation? Certainly, well, what various people around 1960, that was a few years after BCS, answered yes. But in this case, this pairing amplitude, which in BCS is essentially a S wave, essentially a constant angular in angles around the Fermi surface, must be anisotropic. And the result, if the interaction S-wave pairing, so it could not be S-wave pairing as in BCS. The S-wave pairing, if we have a repulsive interaction, the S-wave pairing essentially scales to 0. And in low order perturbation theory, we would just have a Fermi liquid. But there were speculations by Kohn and Luttinger that there could be solutions to the gap equation caused by the singularities in Q space associated with the sharp Fermi surface at low temperature. This could lead to anisotropic solutions of the gap equation, but the TC they predicted was very small. So again, this idea came in 1960, but for a long time, there were no candidate superconductors around. So some transition metals were actually BCS-like superconductors. Others show magnetic order, and magnetic order can have TCs like iron up to 1,000 Kelvin, which was very high. But there was no sign of unconventional superconductors, that's to say non-S-wave superconductors. But a breakthrough came around 1980 in two directions. Frank Steglich in Germany discovered heavy fermion metals, which were low-temperature superconductors. Jerome and Beschard discovered organic metals, organic materials which form metals. These, for example, the heavy fermion metals, these are intermetallic compounds with rare earth elements. Now, the rare earth elements have localized, partially filled F-electron shells. So the F-electrons are concentrated near the nuclei. So there's a strong repulsive interaction since they have strongly localized wave functions. But the heavy fermions occur through the weak admixture with the conduction sp electrons, which are much more mobile outside these ion cores. And this class of material were discovered around 1975. So we can have, in these materials, a narrow band of slowly moving electrons. The heavy mass, they're called heavy because the mass is high, but actually it doesn't mean that they're any heavier than the regular electrons, just that they move more slowly. So, and some then became superconductors. So there was speculation then that they could be unconventional superconductors, and that is generally believed today. So there are quite a few of them. This was the one that Frank Steglich discussed first. See, here is the cerium atom. Here is a two-dimensional one with planar cerium atoms. Here is a praseodymium scudorite. Here is a uranium compound. See, many different ones. This is another famous one, uranium platinum-3. This was the one that Ott worked on in 1981, uranium beryllium-13. So there are many of them, but the TC is always very low in the single degrees Kelvin. The other one material, these organic superconductors, these are materials where we have large organic molecules which can arrange themselves in layers or linear stacks. These they get simple band structure because the band structure is associated with an outer electron which is delocalized over the whole big molecule. So the Fermi energy then, Fermi level, cuts through a narrow band of these localized electrons, that are delocalized over the molecule. And you can find, again, many of them. Here's a list of ones made out of this particular molecule, this so-called ET molecule. And you see, well, some of them get up to 13 Kelvin. But again, there's a lot of them. And these are well described by a single band Hubbard model. That's a model where the interaction is localized on the site. And with a narrow bandwidth, because the overlap between these big states extended over the whole molecule to a neighboring molecule is small. So they move in a narrow band in both these superconductors with small Tc, so that the conduction electrons contribute little to the total energy, and they basically don't determine the crystal structure. So it's clear then what we need for higher Tc values, we need conduction electrons that move on higher energy scales. And for this, the transition metal compounds are ones because the d electrons on the one hand are partially localized, they have more stronger interactions, but on the other hand, they're not nearly as localized as the F, so we can combine strong interactions and wider bands. So, but for many years, this was simply a pipe dream, and there was no candidate for high Tc superconductivity. So this changed in the mid-1980s. The first one was discovered by Bednorz and Mueller, lanthanum copper oxide. And then it was quickly followed by this famous discovery of Paul Chu, who I'm sure has been well known here and well remembered for founding this institute, and M.K. Wu, who's now in Taiwan. So this is a similar compound in the sense that it has this plane here of copper O2 plane. But the important thing here is that Tc was 90 Kelvin. This is taken a figure from their original paper in 87. It shows here the resistivity going to 0. This is above liquid nitrogen. And this is the effect of magnetic fields suppressing the transition temperature. But this was a spectacular discovery because, of course, liquid nitrogen is readily available. It's like liquid air. So it expanded the possibilities of application enormously. Now, so let's look more closely at this material. If we look at it, then the valence state of the copper is 3d9. That's to say, normally copper as a metal is 3d10 with an outer electron, but here, if we put it in an oxide, so we take 2 electrons away, we have 9 electrons left, and the structure here is a planar structure with the coppers in the center and oxygens in between, forming in this plane a nice square arrangement. But the coppers actually form a full octahedron, which splits the 3D shell into a lower group of 6 and an upper group of 2. And these outer 2 ones here, these higher energy 2, hybridize most strongly with the oxygen because these are the wave functions that point towards the oxygen. Oxygen has a D state here, so we have strong hybridization. And this material also, the octahedra are not perfect. They elongated along the c-axis, which means that this material here is more strongly hybridized, and we're looking at the anti-bonding band, so this is the highest band, so comes out with this x squared minus y squared. So we get a single band from looking at the band structure, and the question is, even with the strong interactions, as you mentioned in the introduction, a paper with Fuchun Zhang soon after these materials were discovered, show that even in the presence of strong interactions, this state, when we take an electron away, copper 3+, is still a spin singlet and not a Hund's rule triplet, which we might have expected, because if we take one away, we could have had 2 electrons in 2 different orbitals. Instead, the electron comes out of the same orbital. So this makes any holes or any extra electrons that we remove very mobile. And so we have a material which has a single isolated band here at the top of the anti-bonding bands between the copper and the oxygen, which is nearly half filled. As we dope it to get the superconductor, we remove electrons, or as we say, dope holes into this material. So the cuprates then have this interesting phase diagram. Out here, when the doping is 20% or more, essentially, we find the superconductor, and we find the Fermi surface of the metal agrees with this picture of a half-filled band, can be directly measured in ARPIS or the Has-van-Alphen quantum oscillations. So out here, this single picture, this half-filled band is exactly a nice description. Over here, some more complicated stuff goes on, because if we don't dope it, this material is in fact not a regular insulator, but a Mott insulator. It also orders antiferromagnetically, but that is not the reason for its insulating behavior. So let me explain to you, those who maybe do not know what a Mott insulator is. This is a case where electrons are localized in real space when the Coulomb interaction repulsion becomes large. So the bands would still be half filled, but you would have a metal. And you can think of this most simply if you consider a lattice of hydrogen atoms. This is a theorist construction here, and you just pull the lattice apart so that the distance between the lattice parameters, say, becomes bigger than the Bohr radius. Now then, to make a charge excitation, you have to move an electron from one to the other. In the ground state would be 1 electron neutral hydrogen atoms, 1 electron on each side. But if you move one from one side to another, it costs a lot of energy. It costs, in fact, close to a full Rydberg to do that. Now, you could gain energy back by allowing these to hop around. This empty side hops by an electron moving onto it from the neighbors. But the energy you gain back from hopping is related to this overlap. And the 1s wave function has a radius of the Bohr radius. So when you pull apart, this energy goes down. This one doesn't change. So at some point, you get to a situation where this energy cost to create these excitations in the first place is bigger than the bandwidth and any energy you can gain back. So this is a Mott insulator. So this is not an insulator from the Bloch rules that I mentioned earlier, but an insulator because of this huge Coulomb interaction. And the low energy physics of this material then is purely spin degrees of freedom, because every one of these hydrogen atoms, of course, has an electron spin, and these will interact via a Heisenberg interaction at low temperatures. So very, very soon after the discovery of this first material, Phil Anderson came up with this beautiful idea that, in fact, this type of antiferromagnetic Mott insulator might still be on the verge of superconductivity if you doped it. And his argument was that if we consider this material as a superposition, a quantum mechanical superposition of singlets, and we remember that a singlet for a pair of spins, of course, has a huge energy, which nowadays we said that this is entanglement energy. It's 3/4 J, whereas the classical energy is only 1/4 J. So if you had a situation where you had essentially a network of these singlets, but then you make a superposition of all the different possible arrangements of singlets, and then you take particles out, there is a close analogy between the BCS wave function when we force all the electrons to sit no more than one electron on the site, and this arrangement, this resonating valence bond of singlets. So looking at it this way, this gives you a hint that this material here, the magnetism in this material here, may be making it on the verge of superconductivity. But this theory is beautiful, but as a beautiful idea, but it's turned out to be hard to work out with in practice. So let me look at the superconductivity in the cuprates from the other side, namely when we have a lot of holes, and there we have a more conventional full Fermi surface measured in the experiment. And let me point out that these Fermi surface is kind of anisotropic in K-space, because this band structure here, these points where the band structure, this is just a quarter of the zone here I've shown, approaches the edge of the Brillouin zone here, the Brillouin zone here, there is a saddle point. And in 2 dimensions, that gives rise to a Van Hove singularity. And so we have a great enhancement of the density states in this part of K-space. So we have something that is rather not isotropic in K-space, but enhanced. So if we want to do unconventional superconductivity now with repulsive interactions, then as I said before, this sort of gap equations that we had before, this is now the linearized gap equation which determines Tc, has a problem, because if we were to take psi here and psi here with the same sign, and we have here a repulsive positive interaction, then this minus sign means we can't get a solution of this linear eigenvalue for Tc. So we have to, as I said before, do something to change this sign make a sign change in this amplitude, no longer a constant around the surface, but look for some irreducible representation of the crystal point symmetry, which has sign change as a function of angle. And this is a simplified view how this works out so well in the cuprates, because the pair scattering that I showed you here, if we start with a Hubbard model, then it's essentially a delta function which is essentially constant in Q space. But if you calculate the Coulomb effect of a Coulomb interaction in functional RG, just in the lowest one loop, you find it develops structure in Q space, and it peaks up at pi pi. But pi pi is an integral exactly connecting these points of the high density estates that I said. So if we simply take this wave function here and map it around these areas, then we have a situation that we can get a nice solution if we have the sign here opposite to the sign here, because then if we just concentrate in the simplified view on these regions, we have a psi x coupled to minus a psi y, and a psi y coupled to minus x. So we get a good solution with a high eigenvalue where these two x and y are opposite. So this is says that this superconductivity should be D-wave. It should have this extra phase, and this was then verified by beautiful phase-sensitive experiments that I don't have time to go into in the mid-90s. But remember, but one thing I would point out, this nice analysis only works in 2 dimensions. If we had a third dimensional, like a 3-dimensional cubic with another saddle point up here and up the z-axis, well, we can't have all of them exactly opposite signs because this one cannot be opposite sign to both of these at the same time. So 2 dimensions helps. And that's so, as illustrated here, 2 dimensions helps. So, having explained really why the superconductivity is high, has a high temperature in these materials, you might ask, why is it subject still so controversial? You've probably heard that there are still lots of different points of view, but actually the controversy is not so much about the superconductivity, but about, well, about other aspects. But first of all, let me explain the difference. I mean, why this material can also, another reason for it to be controversial is that although there are many cuprates, they're all variants on the same theme, namely lightly doped copper oxygen planes. Most are strongly disordered, a couple are clean. But there are many experimental techniques, but not all experiments can be performed on all of the cuprates. Like key experiments, ARPAS, STM, you want a good surface. Only some of them have that. For others, like neutron scattering, you want large samples, so this is another group of them. So it's a data-rich field with a large collection of experiments and which continue to have surprises, like in the last few years there's been some surprises. So a successful theory you need a successful theory of strongly interacting fermions, which should explain all of the experiments. As I said, the controversy is not so much on the superconductivity per se, but also, for example, on the nature of the pseudogap, which was on the previous slide that I showed you, where the superconductivity still in the dope region went down, and where we made a transition to a precursor of this Mott state. So, and yet this whole business of reorganizing the Fermi surface seems to occur with short-range order. So there are many different points of view, and Fuchun Zhang and I, during our time here, have been discussing how also about this problem. So it's still a problem of the pseudogap, which is not certainly no agreement on already today. So let's come to the main, which is the main thing in my talk all the time is coming. Why are the cuprates so unique? Well, of the transition metal compounds, only these iron pnictides, also discovered more recently, which have, however, only 50 degrees, so they're not, but the maximum TC is almost a factor of 3 lower than the cuprates. So cuprates are, as I said, 3D1 oxides. Without doping, they're a spin-a-half Mott insulator. And when we hole dope, we change the number of holes from 1 at the Mott insulator, we increase it in the 3D shell. So you might think, well, if we put in 1 hole and we get superconductivity, let's look at what happens if we put in 1 electron in the 3D shell. That again will be an S equal 1/2. And instead of having 1 plus X holes, we have 1 plus X electrons. Well, that brings us to a set of compounds known as the vanidates. Well, let's take a look at these vanidates and see what happens. So we now have this 1 electron down here, rather than 1 hole up here. Now this is in a set of orbitals which don't hybridize as strongly as those ones with the oxides, because now the maximum in XY is pointing towards the center of an edge of the octahedron. So these are the d orbitals that point towards this edge here. And as a result of that, these materials crystallize totally differently. They form a line of octahedras sharing edges, and nice lines like this. And they can be metallic. VO2, this is the structure here of the 3D1, here actually is metallic, but only slightly above room temperature. If you cool it down further, something drastic happens. When it's metallic, this is what band structure shows you, it agrees with it being a metal. But the fact that we have these orbitals here, these pointing towards these edges, and these edges are obviously more strongly coupled in this crystal structure, this lower band here is mostly composed of this XY band. So, but when you cool this material, well, something drastic happens already just above room temperature. You get a huge metal insulator transition. The metallic state doesn't survive. Instead, this nice linear arrangement of vanadiums turns into a set of dimers. These move together to form dimers. And again, it's this 3J/4 that I mentioned earlier, this singlet binding energy, which is doing now something different. It's forming pairs, because now we only had a line of atoms, of vanadium atoms, whereas in the other case we had a square lattice of coppers. So now it just gains this singlet energy by distorting it, forming a lattice of dimers, and that can open up a gap. So there is a large lattice distortion involved, and that, if you try to dope it, can cause problems. So let's see, can we dope these materials? Well, the answer is yes. We can, to a certain extent, dope these materials. It's been known for many years. The chemists have called him, Magnesium was a Swedish chemist who discovered a set of compounds. But now here is VO2. If we add one electron per vanadium, 2 electrons is V2O3, and then you have a whole series of crystal phases, VNO2N-1, sitting in between. These are these Magnesium phases, and they consist, you see, of, if you like, some kind of phase separation. You have N of these octahedra, but N-2 of them form these nice V4 plus chains that were the singlet dimers, and the other two, because there's now some 3 plus vanadium sites, sit in the shear plane. So there is like a real separation into differently coordinated sites, with some with 3 plus and spin one side, some with 4 plus. But there is one of these ones here. Well, you might say L is not lost. There's one of these ones for some reason, which I don't understand, which actually stays metallic. All the rest of them have a metal insulator transition shown in red here, and ordering of these vanadium 3 plus spins. Well, let's take a look at this one. Well, this one, which is metallic, this was the more recent work done by Paul Canfield. If you look at the resistivity and the susceptibility of this material, it's rather a curious metal with an almost Curie vice-like susceptibility, very unusual for a metal, showing that there is basically sluggish motion of the electrons moving these 4 plus and 3 plus around. But suddenly when the magnetic ordering things pick up, and we get a nice T-squared law here, but no superconductivity. And so this low temperature phase here doesn't show superconductivity. And it gets even worse. If we can put pressure, people then later put pressure on this phase here. It's an antiferromagnetic metal. They could suppress it. It keeps a T-squared low at low temperatures, which indicates it should be some kind of, or signs of a Landau Fermi liquid. And in many cases, I didn't mention it earlier, but in the heavy fermions, when you get rid of antiferromagnetism, that's when you get superconductivity. No such luck here. So you see that this 3D1 and 3D9, the crystal chemistry is very different. And you can't simply say that you can go, you might think to go from 1 electron to 1 hole, there would be a close comparison between the two. That's really just not the case. So if we look at the comparison between cuprates and vanidates, or also nickelates, we see cuprates are described by a simple model, a single band Hubbard model on a 2D square lattice. They're highly quantum because 2 plus and 3 plus have the same local symmetry. There is no Jahn-Teller effects when we have partially, to lower the symmetry, when we have partially filled shells. It has spin a half, a highly symmetric lattice. And all of these things, you see, favor superconductivity. Favor quantum mechanics. They favor a quantum mechanical site, and not essentially classical site associated with coupling to the lattice. And it's this quantum mechanics, of course, which drives superconductivity. There's no classical analog of superconductivity. It's quantum mechanics. And this is then completely different to what we've seen in the vanidates. In the vanidates, we got this singular dimer chain, complex structure, site differentiation between the 4+ and 3+ when we doped. The nickelates, it's the same. That's one less electron than copper. And it has at half filling an S equal 1 nickel 2+. So that's the state we don't have in the cuprates. It's this S equal 1. So then if you take out an electron out of nickel, you get a Jahn-Teller effect. You get a big distortion of the octahedra, which self-traps this polar on here so it doesn't move freely. So these materials just behave very differently. So the conclusion is if we are looking at 3D transition metal compounds, their higher bandwidth, which we were using to get higher TC, however, introduces an unwanted complication, namely their electronic structure is related to the crystal structure that they form. These two are not independent. They're strongly coupled by you minimize the total energy by adjusting this with this. And so you cannot simply say, I'm going to have a nice Hubbard band with a nice symmetric lattice. This low energy effective electronic model that you're going to get cannot be realized independently of the crystal chemistry. It's the crystal chemistry which determines for you the nature of this low energy structure. So we cannot just dial up any lattice we want and any interaction we want. That's what you can do with cold atoms. But in the world of condensed matter, you just can't play that game. So it's very different. So conclusions number 2, well, any future directions? Well, this is a hard one, knowing what might be interesting. I mean, there are a couple of things which I think could be interesting. One is if you could control and structure these artificially, these copper oxygen planes, for example, you could substitute zinc plus, which would be the insulating, for the copper 2+. And this way you could hope to pattern. For example, you might be able to generate a lattice of cuprate quantum dots where you would be exchanging pairs and not single electrons in the standard quantum dots. I mean, that could be interesting. Or another idea that I got from Gabe Epley, who's now moved recently to Switzerland, and this is an idea to fabricate donor lattices in semiconductors. For example, the phosphorus dopant in silicon looks like a renormalized hydrogen atom. So if you could organize it on a superlattice of these donors, then and you could change the lattice parameter, etc., maybe you could get some material which on the one hand had superconducting properties and the other hand could be mapped in with the semiconductors. So I mean, there are interesting ideas around. I mean, up till now, nobody has been able to order you can dope phosphorus into silicon. People have been doing it for years, but it all goes in randomly, and you don't get any nice possibility. This disorder is just too big. So these are possible things. So I see my time is up. So I'd like to thank you for your attention, and I'll be happy to answer any questions you have. Thank you. Okay, go ahead. You can see if there are any questions.
But any questions? So may I have a question?
Sure.
For this cuprate, you emphasized this whole doping side.
Yes.
So how about the electron?
Well, the electron side isn't so interesting. You can dope, but the antiferromagnetism lasts longer. On the electron side, if you dope an electron, then you're going to copper 0, in other words, copper without or copper 1 plus, I should say, which is a copper with a filled D shell. So that actually would like to have a different orientation, a different surrounding of the oxygens. Generally, if you form such copper 1 plus compounds, they will form with only 2 oxygens of 1 and below and not an octahedra. So you can expect some kind of lattice distortion with it. And the antiferromagnetism lasts longer. The superconductivity exists around about where the antiferromagnetism disappears. It's not as high and not as robust. So that's why I focused on the hole doping. That's the much more robust superconductivity.
So who?
Thank you. That was a really extensive, thorough review of BCS as well as the rates. And I think part of the issue is the perfection of the material. So, and that is doping the cuprates precisely in order to strengthen the superconductivity or the TC. What you propose for future directions are both extremely challenging. Either to make an ordered superlattice of phosphorus donors in silicon or do zinc substitution. So of the techniques that have been used to make YBCO, the cuprates, or any of the cuprates that you know of, they've done MBE, a variety of techniques. Is there anything that you can think of that is an approach that would take us in the right direction of getting suitably perfect materials? Or can we learn something? I hate to go to the two-dimensional materials, but the advantage they have, like graphene or polydisulfide, the advantage they have is that we can get layers that are not perfect, but once we get layers, perhaps we can play games with trying to change coupling, the electron-phonon coupling. So you have an extensive knowledge of the cuprates and how they were synthesized. Is there any approach there that would allow us to get a structure where we might have better control?
Actually, as it turns out, and it's, I would say, not fully understood, but as I mentioned earlier, a number of the cuprates are quite disordered. This Bisco, which is a cuprate with a maximum TC of 90 Kelvin, 2-layer Bisco, is a very dirty material. But because we're dealing with strong coupling, it survives. I mean, the weak coupling, there's analysis going back a long time showing that this type of state shouldn't survive, but it does survive. But so it seems to be more impervious to this disorder. But if you look at the highest TC of the cuprates, that is the mercury cuprates. Now, these ones are actually very symmetric, and the planes are very clean because these are doped by putting extra oxygens in the reservoir part of the structure between the copper oxygen planes. And in fact, if you just do a single plane, this is mercury 1201, that has a TC as a single layer material of 90 Kelvin, and it has perfectly flat planes, and in the NMR, it doesn't show much disorder. And there's also a cuprate. It's a 2-layer version of this YBCO, which I showed, which shows very sharp lines in NMR, and it's a well-ordered single crystal. It is not, you don't have to introduce it. The material itself is self-doping of the planes. So there are some examples and where we do see quite pristine structures. I mean, and the lead one, of course, goes up to, without pressure, to 133 Kelvin for 3 layers. Not the lead, I keep saying lead, mercury, one up to 133 Kelvin. So I think that the limitation on TC is not disorder in the structure. I mean, the mercury, which has the highest ones, really have very nice planes. And it's, I think that's just, from the coupling constants and everything, is just the maximum that you can get out of it. So, of course, I mean, they are difficult to grow because oxygen is strongly interacting material. So it's different than semiconductors. So I think in the future, one can hope maybe that crystal chemists will figure out a way to grow these things better. But in general, many of these ones are quite disordered.
Any more questions? I have one more.
Sure.
Is it possible to electron dope any 3D8 materials?
Any which?
So for this copper, you have this 3D shells with 9
Yeah.
electrons, but you also have materials with only 8 electrons.
Nickel, yeah.
Nickel, you mentioned.
Oh.
So electron dope it
Yeah.
and make it something like.
Well, I think you run into the same problem that you see the D8 state in nickel is a spin 1 state, and it has a very good cubic octahedra. Now, I said that in the cuprates, the octahedra is elongated. So in nickel oxide, which is D8, you have this very beautiful cubic octahedra. And then, so now if you put in an extra electron or you take out an electron, you've changed the local symmetry, and the lattice around it relaxes, and you get self-trapping of what's called a small polaron. So nobody has found any superconductivity or even conductivity, metallic conductivity in the nickelates. I mean, there was some speculations around about it, but it never went anywhere, yeah. Yeah.
Thought on the superconductivity is still very low TC on the chromium related material.
Sorry? Which,
Chromium, like arsenate.
Chromium?
Yeah.
I don't know that one.
There it's still lower TC.
I see.
Yeah, but it's a superconductor. One was reported from Zhejiang University.
I see.
The other was even earlier, but more simple, lower TC, in IOP.
Oh.
So I think pairing the electron should be on the chromium side. That would have some hope.
Well, I have to talk about it. I don't know about this. I mean, there has been a report recently of 170-degree superconductivity in a hydride material, but under gigantic pressure. What is it, 170 megabars or something? And of course, there has been speculation from Neil Ashcroft going back many years ago that if you could have a simple metallic hydrogen, because of the high phonon frequencies, because hydrogen is so light, that you could hope to get superconductivity that way. And then hydrogen doesn't like to form a simple metal. Hydrogen forms molecules. Solid hydrogen is a bunch of molecules. So, and then if you put pressure on it, it forms all sorts of complicated structures and never forms a nice, simple, high symmetry structure. So maybe this particular hydride at this enormous pressure does something like this magnesium diboride that has some place where there's some hydrogens rattling around at high frequency and coupling to the rest of it. I don't know, but But since it's at such a gigantic pressure, I don't think it's going to solve the problems of getting better superconductors so we can use less electricity. Yeah.
So thank you. If there are no more questions, let's thank Professor Rice again.
Okay.